Welcome, everyone, to today's CDAC webinar. It's my pleasure to introduce today's speaker, Sario Fensin from Los Alamos. Sario is an expert in the dynamic behavior of materials, specifically metals and alloys, and how the microstructure in these materials control damage and failure, and the roles of heterogeneities and defects. She does experiments as well as is engaged in modeling and in the development of improved strength and damage models for materials. Sario has a bachelor's in chemistry from Mount Holyoke and also a bachelor's of arts and sciences in chemistry and physics from Mount Holyoke. And she got her PhD in material science and engineering from UC Davis. Sario joined Los Alamos in 2010 and shortly thereafter became a member of the technical staff. And for the past 6 years or so, she's been a team leader in the quasi-static and dynamic behavior of materials and project lead for strength and damage in dynamic materials in that program. And she's also part of the Center for Integrated Nanotechnologies at Los Alamos. So thank you very much for agreeing to give this talk. We look forward to it.
Thank you, Russ, for that introduction. I'm going to share my slides, and then we will get going. Can you see normal slides or presenter view?
That's a presenter view, so I need to switch it.
Okay, I'll just go back to. All right.
Good.
Thank you, Russ, for inviting me to give this talk. I'm glad that the cancellation worked out for me. Before I give the talk, I kind of like to talk a little bit about my journey to Los Alamos and how a chemistry and physics undergrad ended up in material science at Los Alamos. Russ kind of already gave where I did my degrees, but one of the things I think that's significant is the reason I got into R&D is I was looking for a summer internship the first year of my undergrad at Mount Holyoke. And there was a scientist, Maria Gomez. She was a new professor. She had a job opening for somebody to do computational material science, specifically looking at proton conduction in perovskites using density functional theory. Let me tell you, I knew nothing about density functional theory. I knew nothing about Unix. But being who I am, I applied for that research position. I got that position. And that's what really kind of set me on the path to where I am today. After I got that internship with her, I ended up working with Maria extensively throughout my undergraduate career, ended up doing an undergrad thesis. She was the one who got me an internship at Los Alamos, where I became interested in material science, especially associated with radiation damage in materials. That set me on the path to get a PhD with Mark Asta, where I worked on grain boundaries, which again, I had no clue what grain boundaries were because I was a chemistry and physics undergrad, but I made that switch. And then eventually I met Rusty Gray at a Gordon conference and ended up doing a postdoc with him in experimental shock physics. Kind of big changes in my life. And the reason I bring that up is I always tell my students, look, it's your ability to learn and adapt that is going to get you places in life. And I like to mention that because none of us kind of learn, maybe unless you're in Russ's group, most of us don't really learn about high pressure science or shock physics in general. There are very few programs in the US that cater to that. But as long as you're smart and you can pick up skills, like that helps you throughout your life. So right now, Russ mentioned I run a team where we look at quasi-static and dynamic behavior of materials. Really, if you look at a high level, what we look at is structure property relationships in materials. So as I change the microstructure of a material, let's say through processing, I could do heat treatments, I could roll materials, I could additively manufacture them. how does that change in microstructure affect its mechanical behavior? That is really the bread and butter for my team, with the emphasis on high strain rate behavior of materials. People who are material scientists probably know, you bend and break materials at really low rates. That's our quasi-static testing. That's just one of our old kind of hydraulic load frames we use for a lot of our compression and tension tests we do. And then on the bottom is an image of old Hopkinson bar system we had, where we can do testing on materials at strain rates of 10 to the 3 per second, 10 to the 2 to 10 to the 3 per second. The reason strain rate matters is because deformation mechanisms in materials are very dependent on that time scale. If you give material more time to deform, like you do in quasi-static loading, deformation mechanisms are going to activate, different deformation mechanisms are going to activate, and the behavior is going to be different. Well, why do we do all of this stuff? It sounds kind of boring, bending and breaking material. The reason we do this stuff is a lot of the data that we collect at a variety of strain rates and temperatures goes into development of models that describe the deformation and damage behavior of materials under loading. These models are then used in certification of the US stockpile. In fact, these models are critical for certification. So that's why we do a lot of work collecting information on these materials as a function of time, temperature, strain rate. We can perform work on depleted uranium, U6 niobium, beryllium, high explosives. We just don't work on plutonium. Thank God for that. We also do a lot of work in the nuclear energy area. We have some unique capabilities where we can do testing on fuel at really high temperatures, up to 2000 degrees C. And we can also go to really low strain rates of 10 to the -5 to 10 to the -1 per second. That's important because in NE, when you're looking at fuels, be it for reactors, be it for space reactor applications, these materials are going to be subjected to really high temperatures. So we kind of build that capability. And this is another part of our team where, in addition to our conventional mechanical testing on materials, we also do a lot of shock experiments on materials to parameterize, to measure the equation state of materials, to look at how materials fail, especially as a function of the microstructure. We look at ejecta, that is material coming off the surface, which is shown in the bottom movie that is playing on my screen. Basically, there what you saw was as a demonstration, we had machined a very rough surface on a sample. The shock came from bottom to top, and we're doing some high-speed imaging to look at how those perturbations invert. Right here, you'll see invert and cause material jets to be ejected from the material. That's part of the dynamic properties in materials. We have 3 gas guns, 180 and a 19 millimeter gas gun. What really you need to know is that allows us to go from 50 meters per second to about 1200 meters per second in terms of velocity and pressure ranges. So when we're collecting dynamic property data, we can actually investigate a large range of pressure, which is important when you're trying to parameterize some of these properties. The cool thing about our gas gun, the unique thing, is that in addition to collecting photon Doppler velocimetry data from the back surface of the sample, we also actually recover our material. So this is one of our recovery chambers on an 80 millimeter gas gun. Essentially, this is the small tank that goes into the big tank. After our sample gets impacted, we soft recover it within this tank. Then we can section it and look at, okay, well, the material failed here, here, and here. Perhaps if we modified the microstructure in A, B, and C ways, we can improve the properties of this, dynamic properties of this material. So that's the unique thing that my team does. I like to joke that most of people in my team are actually material scientists, and we just look at shock as a way of, subjecting your materials to some interesting loading conditions to see how they fail. That's why we also have that low velocity gun, which a lot of people don't tend to have. Here is just some of a table showing our capabilities. And I don't know what everybody's background is here, but I know that when I first started working on shock or dynamic loading, I had no clue what we were talking about. So I kind of like to talk about, explain what shock is or dynamic loading is. How do you get failure under it? Excuse me, I'm a little under the weather, so my throat hurts when I talk a lot, so I'm gonna drink some water. So a shock event is anything that creates a perturbation in your material that travels faster than the speed of sound. In reality, how we induce that shock wave in your material depends on your application, but it can be done in multiple ways. A lot of the applications I'm going to talk about are going to be related to gas guns, but you can use high explosives to drive a shock into a material as well. But essentially, let's assume this light gray block is your material of interest. Usually in a gas gun, you have a breech where you have pressurized high pressure gas. You have a projectile in front of that breech, which when you release that pressure, that pushes the projectile down a barrel that then impacts your sample. When your sample gets impacted, it essentially gets compressed. And if you were looking in the time space diagram, this x-axis is along your sample and time is just time. At zero time, there's nothing going on. When you get impact on the sample, you generate a shock wave in your target. You generate a shock wave in your impactor. These waves get to the free surface and get reflected back as a release wave. Essentially, what they're doing is trying to bring your target down to zero stress. When these waves intersect in a region, and you can imagine already by changing the ratio of the thickness of target to impactor, you could essentially get these waves to intersect anywhere or not intersect at all. But because a lot of the work we do in my team is associated with spall failure or damage in material, we tend to want these waves to intersect by design so that we can open regions of failure in the material. This is what it looks like in a schematic form. You might get a state of tension where these waves intersect, and that's why you nucleate voids. Now, there's spall of two types. One is you impact the sample so hard that it falls into two pieces. That's full spall. Or the other one is when you get very early stages of damage. That means you have really early stages of void formation. And if you were looking at a material under the microscope after you've picked it out of the gun, you sectioned it and you prepped it, what you would see is these voids kind of located at different features in your microstructure. So this, I think, was copper, if I remember correctly. You can see different grains here, and you can see a lot of these voids are located at grain boundaries and triple junction within that region of tension. You don't just get damage all over the material, just in a narrow band. For most people or most labs that do this type of work, the primary diagnostic is photon Doppler velocimetry. And what that is, simply speaking, is you shine a laser of known frequency on the back surface of a sample. As the sample starts moving, there's a frequency shift. Knowing that, and once you measure that frequency shift, you could do a Fourier transform and essentially get the velocity at which your sample is moving. So I'm going to run through an animation on the right side here, where you're going to see that space-time plot that I showed you, and what that might look in the velocity time space. You get impact, and here's your laser point, by the way, the PDV point that you're measuring at the back surface of the sample. So as the sample gets impacted, the shock hasn't reached the back surface yet, So essentially, your velocity is zero. The back surface hasn't caught anything. When, if your material uh, I don't know what happened. My computer just quit. Can you hear me?
Yes, I
Yeah,
can hear you.
Okay, I'm gonna share my slides again. So sorry about that.
Okay, I'm not sure what happened.
I don't know. My computer just froze and it just kicked me out, like kicked
Oh,
me out
okay.
of Zoom.
Okay.
Okay, so I think I was here. Hopefully, you guys all heard where I
Yes,
was.
I think that's where we lost you.
Okay, perfect. So basically, the point I was trying to make here is nothing really happens. You don't measure anything in the PDV until something happens at the free surface. So these two waves get to the surface, the material gets shocked up, then the signal stays constant, nothing is happening until this release happens and the shock gets caught up between this small scab and the free surface, and you get this ringing type behavior. So usually this is the primary diagnostic used in shock experiments to understand the dynamic behavior of materials. Like I told you, in our team, we kind of go beyond that and do recovery of samples. The other interesting thing is in a lot of the metals, when you do normal mechanical behavior measurements, there's a yield strength, the elastic to plastic transition stress. Similar to that, there is elastic to plastic transition under shock. That's called Hugonio elastic limit. That can tell you a lot about your material and the deformation mechanisms that are being activated. You can use this free surface velocity plot to also calculate stress required to nucleate voids. Again, that's an approximation. Basically, you can look at the difference in velocity between here and the top point and convert that using the bulk sound speed and density of the material into a stress required to nucleate voids. That gives you an idea if I make a material using additive manufacturing versus conventional manufacturing, does that really affect the spall behavior of the material? Why do we care about dynamic behavior of materials? Well, there's so many applications. A lot of them are within the DoD, but also you can see that in our regular life, a few years ago, there was, maybe it's been a decade or so now, but there was that plane that had to land on Hudson River, and that's because birds flew into its little engine and caused a substantial amount of damage. So you can imagine if you want to make materials that are more resistant to damage, there can be multiple applications in various industries, including car industry. Now, in my team, of course, we can't like go and do full scale tests. We can't really, crash 100 cars like the car makers do, or, have hostile encounter with actual vehicles in the DoD. So what we do is we do a lot of small scale lab testing to kind of link microstructure to failures so that we can make better materials. So today I'm going to talk about an example that we worked in our team related to joining of different materials and how that process itself can affect the dynamic properties of materials. So most of you who are engineers know that it's very rare that you'll have components made out of a single material. You can have coatings, you can have materials in nuclear energy where you're welding things together. Regardless of the technique, there are a lot of metallurgical challenges in general when you're trying to connect different materials, and those interfaces between materials are what end up dictating the lifetime of that component a lot of the times. There can be different thermal expansion between materials. Certain materials might not want to join at all. So that's what kind of motivated our work. Was we wanted to do some fundamental science to look at how do the dynamic properties of a bimetal interface depend on how you join two materials. There are multiple ways you can join materials together. I kind of talked about welding already. But the two that we focused on was diffusion bonding, which is a solid state bonding process. It uses heat and pressure to bond material. So you can have material A, material B. You clean the surface. You want to have some surface roughness. You put them together. You provide some pressure and you heat it up such that these materials end up joining together and forming an interface. This is one way. Another way, I just call it the metal glue essentially, where you take a lower melting temperature material and put it between A and B, again, apply heat and pressure, and that the metal, the braze material in the middle melts and holds it together, hence my analogy with metal glue. But you can also have things like, is shown in this image where you can do some braze welding. Again, the concept is the same, but here you're just directly melting that braze and not really applying any pressure or temperature, more similar to welding. And then, of course, you can have additive manufacturing where you can have a base material and you can deposit any other material on top of it. You can use electron beam additive manufacturing. You can use laser powder bed fusion, whatever is available. But the point here was if I take the same two materials and I change the morphology of the interface between those two materials by changing how I bonded them, would that affect the dynamic behavior? In fact, the first thing we needed to do is pick something that we could do in the lab, some materials that were easily available. So we decided to go with the aluminum titanium phase diagram, aluminum titanium as our model materials. The nice thing is the phase diagram was also pretty useful to us in the sense that there were spaces where we knew that we could form thialuminum 3 between the materials at temperatures that were accessible to us within using the furnace we already had in our laboratory without buying new equipment. So we knew, okay, we could probably form a stable interface between these two materials. But we also wanted to understand, once we do that, what does that interface actually look like? So we did some work and we found that that interface tends to be kind of wavy. And the reason we needed this is if I'm going to try to understand how my interface properties or interface morphology perhaps affect dynamic properties, I need to be able to change one variable at a time, be it the shape of the interface, be it the materials between the interface, be it the interface region thickness. Now, experimentally, it's almost impossible to do. Anything you do to materials to put them together will change multiple things at a time. So in this case, we decided to use molecular dynamic simulations because in a computer, I can do whatever I want, and then we can go back to experiments and try to do some smarter experiments to validate some of the insights that we get from simulations. So those of you who are not familiar with molecular dynamics, it's essentially you're solving Newton's first law of motion, essentially F equal to ma at the atomic scale. You can extract that position time plot like I showed you during the shock simulations. You can simulate the grain structure in a material. Now I'll put a caveat there. When I say grain structure, sure, you can have the morphology of the grains, but we're limited in terms of how large our grains can be. So usually, the grain size is a few nanometers, whereas experimentally, the grains are tens of microns. So the point here is that we're trying to get qualitative insights from molecular dynamics, not necessarily solve the whole problem and get quantitative information. But the nice thing is, once I've run the simulation, I can look at the microstructure, I can look at how much dislocation density is formed in my material under shock loading. Where did my failure form in a microstructure? And I'm going to use that to look at bimetal interfaces. So the first thing when you're trying to put two materials together is, you have to figure out the orientation relationship between the two. So aluminum and titanium were kind of nice. There was a Shoji Nishiyama orientation relationship between the two. Other people had made flat interfaces between them. The lattice constant for these two materials is different. So you can imagine that when you're putting them together, you have to expand one lattice and maybe contract another lattice that leads to the formation of misfit dislocations at the interface. But essentially, what we do is we know that we calculate that strain that will be in both the materials. We put the materials together, equilibrate them such that we form the lowest energy structure. That forms your flat interface. But like I told you, that I was interested in how does that interface morphology or the shape affect the dynamic behavior? And MD lets me do that. So we wrote a special code that lets us essentially change the interface shape in different ways. One thing we did is we formed a wavy interface. This was important because some of our experimental detective work had shown us that a lot of these interfaces tend to be wavy at the atomic level. We also wanted to see, well, what if I don't have these rounded kind of cosine waves and I had a sawtooth interface? Does that help me improve the dynamic behavior of the material at all? Well, what about this square shape? Maybe that would be better. Wider squares or any kind of, you can pick and choose. I won't go into all the details because I have a ton of slides to show you. But when you do molecular dynamics simulations, you need to pick interatomic potential that is actually realistic and can reproduce the properties of the material. So we used an embedded atom method potential for aluminum and titanium. Our cell was 30 by 30 by 30 nanometer cube. Now remember, this is what I was trying to say. Only has 2 million atoms. Experimentally, it's like nothing, right? Like I won't even see this unless I was using a fancy TEM. Even then, like this is really pushing the spatial resolution of some of those instruments. But we're only looking at qualitative insights and not quantitative data here. And I'll show you the experiments we did and how they compared with our simulations. All the simulations were done at room temperature. Another thing to keep in mind is that the strain rates in the simulations that we're running, excuse me, are really high. They're 10 to the 8 per second. And also, before we did the shock simulations, we actually wanted to just look at compression testing between the two materials as a function of that interface shape, because that gives us an idea about how the dynamic response would change. So that's what we're going to start with. We're going to have our two materials, flat and different wavy interfaces. We're going to apply uniaxial stress, so just compress it from top and bottom, measure the stress strain response, along with quantify some dislocation densities as a function of that interface shape. And really, the end goal is if we could make our material stronger by changing that interface shape, that's a win for us. Or maybe the answer is you can't do anything because that interface shape doesn't matter. So we ran our simulations, and I'm not going to show everything. I'm going to focus on 4 different type of interfaces. This is a stress strain plot that we extracted from molecular dynamics. Don't freak out about 6 GPa yield stress because remember the strain rate is really high, 10 to the 8 per second. And yield stress and strain rate have a linear relationship in general. And that's why that strain rate matters, because you have different deformation mechanisms. Also in molecular dynamics, you start with these perfect cells with no pre-existing defects. In reality, most materials have defects. So the 4 different shapes that we looked at was a flat interface, we looked at a cosine interface, we looked at a sawtooth interface, and we looked at a square interface. And the things that we changed is we kept the frequency the same, changed the amplitude, so made the waves kind of taller versus shorter, but kept 3 of them in all these cases. The first thing to notice is that that flat interface in general tends to have a pretty high yield strength as compared to these rough interfaces. In fact, we wanted to understand why. So I'm playing a movie on the right side. The movie you have on this side, the atoms are colored by structure. So green is FCC, red is HCP, blue is BCC, and then gray is just, we don't know what it is, just disordered. And then here it's colored by atom type, titanium and aluminum. The first thing you'll notice is that aluminum is much softer than titanium. So when you're compressing the material, you are getting a mushrooming effect around the titanium. That makes total sense. The other thing is when you go from the flat to these different shape interfaces, you see these lines that are forming here. They're stacking faults, essentially left behind by dislocations that are nucleating at these rough regions of the interface. You don't see them in the flat interface. And what is yield stress if not elastic to plastic transition, and plasticity being defined by nucleation and motion of dislocations? So here, essentially, by looking at the actual movies, we could understand that, okay, having a rough morphology actually drops the yield stress in the material because you have reduced the barrier for dislocation nucleation. The other thing that we got is if you looked at all the different waveforms, to me at least, they look the same, but at this strain rate, but we needed to delve into it more. So we decided to do an in-depth analysis. Sorry, I have to take a break for a second. Does anybody have questions before I keep going?
In the previous slide, you had BCC there listed.
It shouldn't even be forming
Yeah.
because you have FCC and HCP. But you see, Russ, there are some atoms that are showing up as BCC in titanium. Did not make any sense to us, but we left the labeling as it was identified by Oviedo, which I think if we change sometimes it's also the potential, right?
Yeah.
Where it goes into a phase that doesn't really exist. So I wasn't going to pay much attention to it, but what I really just wanted to point out is that you're getting a lot of dislocation nucleation from these rough interfaces as compared to the flat interface where the aluminum is just kind of mushrooming around the titanium.
Right. Okay. Thanks. Yeah.
And remember, like these are all perfect systems that we started with. So there's no pre-existing dislocations. And that's why the yield stresses are really high too. Okay, I'll continue. Oh, there's another question. Go ahead.
Yes, I have a question about these simulations. Have you looked at how shock wave propagates or reflects after it hits
Yes.
the interface?
I'm going to show you in the next few slides. So this is just uniaxial stress compression, but we are also going to talk about shock, which is going to be uniaxial strain. And the reason we did uniaxial stress is before we run, right, we got to walk. So under simple loading, what do these kind of rough interfaces do so we can interpret what we see under shock? So you'll see that too. Okay, so I basically in the older stuff, it seemed we were trying to figure out, well, does the shape of the interface matter if you have cosine versus sawtooth versus square? If I go back and zoom in here, it's within noise, I would say. They look very similar in terms of yield stress. It's not like one is super high versus low. So we were thinking that if you go from cosine to sawtooth to square, maybe it really doesn't have an effect on the stress strain response at the strain rates we're at. However, if you change the amplitude within a certain shape, so for example, in the cosine, if I have a large amplitude versus a smaller amplitude, or 60 angstrom to 30 angstrom, my peak stress would change somewhat. It's a pretty small difference, but it was changing, and we wanted to see, like, why would that be the case? Why would amplitude have an effect at all? So one of the things we measured was the interface length. So in a flat interface that has the shortest interface length, and then of course, as your amplitude goes up, your interface length goes up, and that essentially can be attributed to that to the lower yield stress that you see, because now you're nucleating more dislocations as you change that amplitude. Here's a really good example for the square wave. When you go from like 30 to 60, the deformation, like this is almost like that nanopillar compression test that they do, versus this smaller kind of pillar, which is deforming more or less, like just a roughness, but not so much as its own kind of entity, which we're seeing here. So we thought, okay, amplitude probably changes the response slightly because you've changed the interface length, and again, that changes the deformation mechanisms in your material. Well, okay, well, what about that frequency? If I have just one big rough interface versus multiple kind of perturbations in the interface, and here we just pick that cosine interface. We looked at for the same amplitude, which was 60. We just changed the frequency from 1 to 2 to 3 to 6. And what you see is, and we also plotted the stress strain response of the flat interface as a reference. And what you see is that at an amplitude of 60, if you change that frequency, if you have a single versus multiple kind of waves in there, doesn't seem to have an effect, except you could convince yourself that the lower amplitude, at least like when you look at the deformation, kind of behaves like a flatter interface. But in the stress strain response, that red one is the lower amplitude, and that yield stress is still much lower as compared to the flat interface. So far, what we've seen is if you have a rough interface, that rough interface is going to have a lower yield strength. A higher amplitude interface is going to be a little weaker than the lower amplitude interface. And then the frequency at those high amplitudes doesn't matter. So if you process it in a way where you just have like one perturbation or 3 or 5, shouldn't matter that much in terms of its stress strain response. But what'll change right away is if you have any perturbations at all in your interface. And most interfaces atomically are never flat. The other thing is when you're looking at components, well, you don't just have bimetals nicely lined up with your loading direction. So we also wanted to understand, how does that orientation of the interface with respect to the loading condition affect things? So let me kind of restart that movie. So over here, you can see we rotated the interface Remember, our loading is top to bottom. You're changing the orientation of the interface with respect to that loading condition. You go from completely perpendicular to 100, like to 0 degrees, or completely parallel to the loading conditions that we wanted to see. Does this matter more than that interface morphology or the roughness that we were seeing? And what I could tell you from the stress strain response, if you just looked at this Pmax versus interface orientation, is that the peak stress decreases. You get a lot more deformation as you go from 90 degrees to 45 degrees because you're changing the critical resolve shear stress and nucleating more defects, for example, in materials with the loading. And then eventually, as you keep going up, you activate things like twinning in titanium and maybe even some phase transitions, which, by the way, I wasn't sure if that's real in titanium. But in molecular dynamics, we're at pretty high stresses, but still, that could be because of the potential that we're using. But basically, you can go from dislocation slip to twin nucleation transition as you change that loading orientation, and that seemed to have a much bigger effect on on the mechanical response of the interface. In fact, we quantified the amount of dislocations, and I won't go into it, but basically, I've already kind of told you that as you change that rotation, the deformation mechanisms in aluminum and titanium change. And essentially, there is a sweet spot where you want your interface to be, below which your material is going to be too soft. So if we look here, these are dislocations. You don't want too many, you don't want too little. So probably, I think 60-degree was orientation, ended up being the highest yield strength for the interface. Well, what about the other thing we were seeing is in that flat interface, we would see a lot of sliding between the materials, especially as you were rotating them and you were pushing them, one material would slide with respect to the other. But when you added that rough geometry or shape at the interface, you kind of lock in those interfaces. And you basically stop the sliding behavior. You see a lot more twinning in the material as compared to the flat interface. In fact, here are the stress strain response associated with like a flat interface versus cosine interface as a function of that rotation. And I think, at 90 degrees, the behavior is different, but eventually, if you keep rotating, they both start behaving very similarly. And what that told us is that orientation of the interface with respect to the loading condition will matter more than that exact shape at the interface. What does that mean in practical terms? That maybe that little detail at the interface, if you diffusion bonded it or additively manufactured it, is not going to matter as much for practical applications, at least under uniaxial stress loading. Well, what about shock? And we're going to talk about that. But here, basically, I'm just showing movies where you can see when you have a flat interface, you're getting sliding between the materials. Whereas when you have these perturbations, they kind of lock in the materials together and prevent that sliding. Well, what about shock? So we sort of understand what the interfaces are doing under uniaxial stress loading, but when I go to shock, would things be different? So in this case, before we even started, we wanted to do some shock MD simulations on single crystal titanium and aluminum. We used the same potential, room temperature. We impacted it at 1 kilometers per second. You have the position time plots that I talked about, but here you're just looking at the in your target material. So basically you have a shock in your material that goes to the free surface. You get a release wave, you're getting failure. In this case, this is a single crystal titanium, single crystal aluminum. So shock goes from left to right, and release waves come in. You start forming nucleating voids. And what you notice is that the stress required to nucleate voids in aluminum is about 5.8 GPa, and in titanium is 7.6. So in general, aluminum is going to have a lower spall strength as compared to titanium. That's good to know. So then when we did our simulations with the interfaces in place, and I'm going to have to figure out how to play the movie slower. Let me see if I can get rid of my pointer. Okay. So the first thing we'll do is let's look at our position time plots. If I look at the position and the time, the arrow kind of denotes where my interface is. I have three types of interfaces here. I have a flat interface, and I have two cosine interfaces with the same, with different amplitude and frequency. Remember, larger amplitude is like it's a bigger kind of wave. The trough to peak distance is much larger, and we also change the frequency. And what you see is if you just look at this plot, the color bars are the same scale, going from -4 to 28 GPa. What you notice is, yeah, to me they look very similar. I don't see a huge difference. Maybe I could see a difference here in the tensile wave profile or the plane on the top versus the bottom, but really didn't look very different. So if I get rid of my arrow again, and I'm going to play this movie for you. So if you look, shocks coming in, defects are nucleating, you form voids on the aluminum side. And you know what? Regardless of that interface roughness, you always form voids in the aluminum side. We designed these simulations so the region of maximum tension will be at the interface. But in molecular dynamics, the interface is apparently stronger than aluminum. So no matter what you do, you form damage in aluminum. In fact, when you look at the dislocation nucleation, similar to what we saw under uniaxial stress loading, you see a lot more dislocations nucleate from the rough interface as compared to the flat interface. And while they mattered under uniaxial stress loading, because you had a different elastic to plastic transition stress, under uniaxial strain loading doesn't matter. That impedance mismatch is ruling the day because you're failing in aluminum no matter what. How does this compare with experiment or reality? Because molecular dynamic simulations can have their own issues. So to check that, we actually did some experiments. We made three interfaces. One, we basically took two pieces of materials, we joined them together using diffusion bonding. Then in one case, we made defects in the titanium. Imagine like taking a sharp tool and making a scratch and then doing diffusion bonding. So the interface kind of looked like this versus a square kind of interface. Again, we made the defects in titanium and bonded them together. And we did Gascon experiments again, where we captured this, soft recovered the materials and looked at them after. The first thing, I don't know how to calculate the spall strength in these materials because one of the things that we took advantage of, did I put it here, is there is an impedance mismatch between titanium and aluminum. And we took advantage of that mismatch. As the shock goes from titanium into aluminum, you're going to get a secondary release wave at this interface. And essentially that release wave can interact with the release wave from the back and cause a separation of this interface just under shock. Don't even need to do spall. And that's why you see this type of velocity time profile. And really, it is really hard to get from these. You could take this difference and say that's your pullback strength. And because we were failing at the interface, we could call it the strength of the interface, essentially. And we could see that, okay, this is my flat interface, there's a difference. If I do the shock, if I take the same flat interface and shock it multiple times, there is some variability in what you would call spall strength of that interface. In fact, when we recover our example, we do see that material fails at the interface. But this is really different than what we were seeing in MD simulations. Because in MD simulations, we're always failing on the aluminum side and never on the titanium. Never would be lamination of the interface rather than kind of that void nucleation and failure that we were seeing in aluminum in the MD simulations. Well, that's kind of concerning. In fact, and I'll kind of discuss some reasons we think that's happening. In fact, when we go to the other interfaces and we measure spall properties or like this pullback strength, we see that the strength is very similar on all of these interfaces. But again, PDV is one diagnostic. But when you look at the interfaces and how they fail, you notice that, okay, flat interface was delaminating. Here in the pointy interface, basically coming apart at the interface completely. The interesting thing was when you have the square interface, these vertical regions of the interface are staying together while the horizontal regions are coming apart. That was really interesting. But the thing that was driving me nuts, at least, was, well, what's going on? I don't understand why we're not matching our simulations. Because in our simulations, we had a titanium, we had aluminum. The shock was coming from titanium into aluminum, same with the experiment. So why the difference could be there? So there are multiple things that could be going on. And when I say difference, I just mean qualitative difference. I wanted molecular dynamics to at least show failure in the same locations that we were seeing experimentally. It could be, there are multiple things that could be going on. One, in real materials, we have defects, right? There's in molecular dynamic, I just made this perfect cell with no defects. And so materials already defect starved, and the defects from the interface are the ones that maybe we did see a higher dislocation density in aluminum, where the dislocations nucleated from these rough regions, and they probably acted as void nucleation sites. Whereas, 6061 aluminum one, it's not pure. Second, like it probably has a pre-existing dislocation density. So that's not a mechanism that is activating in experiments. The other thing is, if you look at the length scale of this thing is like 30 angstrom. This cell here, this sample here, this is my 1 millimeter scale bar, right? So what I'm looking at in MD is this very small region if I had to zoom in. There could be strain rate issues. There could be a lot of things going on. So, but I think one thing that we did figure out from looking at molecular dynamics and from looking at experiments was that in general, if you add these rough interfaces in the material, while they might reduce your initial yield strength, they might, depending on the shape of these, improve your long-term ductility or delay the failure in material. At least that's what we're seeing experimentally. Another interesting thing was, depending on how you made that interface, that really mattered too. In cases we put the defects in aluminum, which would be right here, and then we bonded them to try to create a rough interface, what we saw was that aluminum just filled those defects, and then those interfaces essentially just acted like a flat interface. So we could switch on and off the behavior, the dynamic response of these interfaces by having a flat interface versus having kind of rough perturbations at the interface. This is kind of a zoomed in image highlighting the fact that, we had a defect in aluminum. When you basically diffusion bonded them, the defect heals, and everything essentially looks like normally bonded material. So the reason I show this slide, I don't have like the coolest conclusions here, but I wanted to give you an example of work where we use molecular dynamics and experiments to try to design interfaces that can help improve mechanical response both at low rates and then also under shock into materials. But basically, the thing that ended up being interesting is MD shows no change in spall strength as a function of interface morphology. Doesn't matter. It does show varying dislocation density, similar to uniaxial stress response. These are the opposite of what we see in experiments. I kind of discussed multiple reasons, but I think dynamic response tends to be dominated by the impedance mismatch more than the interface morphology. I think this is important because a lot of people are doing research right now where they're trying to do interface engineering between multiple materials to control its dynamic response. And I think what we are saying is it's going to be that density difference between the two materials that's going to be more important than changing the morphology. This also gives us the freedom if we have to join materials that are going to be used in dynamic applications to use whatever technique we can to join them together because that interface structure is itself is not going to matter. It's going to be that macroscopic difference in impedance that is going to play a role in dictating its overall response. Okay, so with that, I'm almost out of time, but hopefully we can do questions still.
Yes, thank you very much, Sario. Very informative and pedagogical talk. It's a great
I
example.
know it's very like academic. I usually like talks with a nice like ending with a ribbon on top, but I sometimes like to give these talks where I'm like, we did a lot of work, we learned some things, but not everything was successful.
Yeah.
But this is
Oh,
how we can use multiple tools together.
right. It was very clear. Okay. Questions, comments from the audience? Just raise your hand, unmute yourself, put your comment in chat. So I was wondering when you're looking at those interfaces experimentally at the end, I mean, you could actually look in greater detail with microscopy for defects and so on, but your conclusion is it's not so much that surface defect structure, it's the impedance difference that's most important.
Yeah, I mean, although I would say that when you looked at that sawtooth versus that square behavior, there is a difference. That sawtooth always tends to come apart, right? Because of the way those
Hmm.
interfaces are essentially lined up with that tensile wave, right? But in the cancellation thing, those vertical regions of the interface kind of kept it together. But
Hmm.
I think the difference is subtle when you look at like that pullback signal. And I think if we were to load them at even higher stresses, they're both going to fail the same.
Yeah, I see. Shafiq, go ahead.
Yeah, so in your simulations, did you try to insert some, let's say, defects and see if you can replicate experimental observation?
We haven't yet, but that was one of the things that, I talked about doing. It can be kind of difficult actually to put in pre-existing dislocations in molecular dynamics. A lot of the times what we will do is like do something, take the cell, compress it or something, generate dislocations, and then shock the material. But we didn't get to that yet. But that is something that's on our to-do list because I do want to reconcile, at least qualitatively, the differences between molecular dynamics and also between our experimental thing. The other thing we're going to try is when you saw the cosine and the sawtooth waves, you saw how there was like no flat interface in between them. But experimentally, the way we ended up making those interfaces, there was like, a serration, a flat interface serration. So we're going to try that too, because maybe it's that flat interface somehow that is affecting or causing it to come apart at the interface rather than in aluminum. So we're going to try some of those things, but we haven't gotten to it yet.
Okay, thank you.
Okay.
And when you're creating that interface experimentally, it's the same relative orientations of the two single crystals. Is that right?
It's not two single crystals, it's two
It-
polycrystals.
So, but in the simulation,
In
you
the
have a nice
simulation,
perfect,
they're single crystals.
right.
Yeah,
So,
that's
so,
right.
so you can look more carefully at that interface and whether there's any kind of, reorientation of crystals, polycrystals on either side of the interface and how that's going to affect the strength.
Yeah, we've been trying to do some EBSD. As you know, it can be tricky to prep both materials for EBSD. So we've been trying to do EBSD on aluminum, then EBSD on titanium, before and after impact, right? To see if there's any rearrangement going on. We've also been doing some kernel average misorientation measurements at that interface to see if we can quantify some dislocation densities, if they're higher near the defects versus away from those kind of rough regions of the interface. So there's a bunch of analysis that we are trying to do, but at least like overall, it seemed that if I want to deposit a material to bond two materials together or do diffusion bonding, the response, at least in the pressure regimes, stress regimes we're interested in, should be similar.
Okay.
Which kind of gives us some flexibility in terms of manufacturing and production, which is good.
Right.
Okay, well,
Any more questions, comments?
it's okay. If people have questions, they can reach out to me on my email too.
Okay, well, we're at the top of the hour, so thank you very much for a very clear talk.
Thank
And
you.
thank you for
Talk to you
agreeing
later,
to do
Russ.
this at last moment. Thank you very much.
No problem. Bye.
Okay, take care. Thank you all for joining us.